Okay, so let's talk about some ray model of light and geometric optics. So what's going on in this room? Well, so the sun is shining, it's bouncing off the walls, it's coming into my eye or the lens of that camera. And actually a variety of ray optics kind of things are happening. So we'll actually give them names. And there are two main phenomena that we care about or the ray model of light is useful for describing. So here's my source, cartoon candle, and that's an emitter of light. It'll kind of be an object. It's actually many, many objects. And a ray of light might be leaving and bouncing off of the wall. Actually, many rays of light might be leaving and bouncing off the wall. That's why the walls look bright. They're not making light of their own. So that is definitely reflection. Or we could have a perfect reflective surface, a mirror, and we'll actually just talk about ideal mirrors, nothing that's kind of a partially mirrored mirror. So that's reflection as well. And then there's another set of phenomena that the ray model of light or geometric optics is really good at describing. So let's say that one of these rays of light goes into water or into, I've got a slab of acrylic here, so acrylic will do this. So the light ray will be bent. So it doesn't bounce off, but it actually kind of kinks as it goes, in this case, into my bin of water, which isn't really that kooky and artificial, because that's exactly what you guys will be doing in Lab 1. So that is what we'll call refraction. So that's the bending of light. And a really extreme and precisely engineered case of refraction is things like lenses. So lenses are refraction as well. So these are the two main topics that geometric optics is really good at describing, reflection and refraction. Okay. So that's happening all over, the light coming off the chalkboard and going into the camera is reflection. It going through the lens of the camera is refraction. And this stuff can be actually rather complicated. So what we'd like to do, and you can think about this, like kind of all of what we'll do in lenses and mirrors is analogous to what you guys did when you talked about circuits, is electric behavior, electric elements and magnetic elements are pretty complicated, but you came up with these idealized things like perfect resistors and perfect inductors and perfect capacitors. So we'll come up with the geometric optics version of that. And the first thing we'll do is come up with a perfect light emitter. So this is what we'll call an object. And it's got this icon, which is just an arrow. So an object is an ideal emitter of light. So the pretentious way of saying that is that an object emits light isotropically from a single point. So this is that point. And what I get to do if I've drawn an object is I can have a light ray come out in a straight line in any direction I choose from the top. So anytime I need a light ray, I can draw a light ray from the top of this. So what's the whole point of the entire arrow if it's just a point? Well, the arrow lets you indicate whether or not this thing is upright or upside down. So the action of sometimes lenses and mirrors will be to invert an object into an image that's upside down, and to have some sense of directionality, this arrow, that'll let us figure out if the thing's upright or inverted after an image is formed. So basically what this does is this tells you how far the object is above some baseline, generally called the principal axis. But light rays only come from the tip. So that's a perfect light emitter. And what's true in actual fact, so for instance, if I have if I have a candle flame or a fluorescent light or something like that, it's a lot of objects. So it's almost an infinitude of objects. So now we want, eventually we'll talk about walls and mirrors. But to start with, we'll come up with an ideal reflector. So an ideal reflector is a plane mirror. And a plane mirror means it's perfectly flat. There's not a single defect on its surface, no bumps, no nothing. And what happens is any light ray that comes in has the same angle with respect to normal as any other light ray that comes in, provided it's got the same angle of incidence. So perfectly flat, and it doesn't absorb anything. So plane mirror has two properties: perfectly flat and reflects everything. or stated otherwise, no absorption. Okay, so these are kind of the basic elements of geometric optics. We'll add a couple more, but objects and idealized things, we'll start with plane mirrors. We'll add spherical mirrors. You won't do anything more exciting than that. And then spherical lenses. So maybe what I want to do is talk about an image formed by a plane mirror. And in fact, this is kind of a roundabout way of defining our next optical element, which is an image itself. So what does it mean to form an image? So I'll take a plane mirror, and I will add an object to it. So this is what I'm going to call the principal axis. And the principal axis is basically, it's got a fancy name, but this is where I locate my image. So where I locate my object. So the base of the object goes on the principal axis, and I can draw any light rays I want from the tip of it. Okay. So what I have is the law of reflection. And we want the angle version of it, which just says theta incident equals theta reflected. Best law in all physics, even simpler than F equals ma. And, they're not even vectors, so it's so hard to screw this up. Okay, so let me draw some, and this is kind of the first lecture where we'll iterate to convergence on what sort of chalk works. Let me figure out what's going on with this, like what sort of image it might produce. And the first thing I can do is I can draw a ray in any direction I'd like. So maybe I could just do this. So I could draw a ray that's parallel to the principal axis. This would be along the normal itself. So if we were to measure this, with respect to the normal is here, comes in 0 degrees from the normal, so it leaves 0 degrees from the normal, and it goes back from whence it came. So pretty boring. I could draw another one that's more interesting, and I could strike the mirror right at where the principal axis crosses it. So light ray comes in there, this is some number of degrees, this would be the same number of degrees, and it leaves like this. Okay? So I got 2 rays that are coming out. So for a plane mirror and a plane mirror only, this will be enough to figure out what's going on with the image that's formed. For spherical mirrors and spherical lenses, we'll generally draw 3. We'll go into the reasons for that when we get to spherical lenses and mirrors, but this is fine for a start. So let's say I'm here, so there's my creepy disembodied eye, and what I see is, sure, I could see this, but then I also see an image in the mirror. So what am I actually seeing when I see an image in the mirror? What I see are these light rays that are bouncing off the mirror. And for me, geometrically, what seems to happen is they seem to be coming from this mysterious point over here. So this light ray that's moving in this direction, this light ray that's moving in that direction, I drew 2, but I could have drawn many more, specifically ones that would actually go into the eye where I happen to draw it. But any of these light rays would actually have the same point of convergence. So note that the light rays don't actually come from here, it's as if they came from here. And this is what you see. So you see a thing on the far side of the mirror that's about the same height as the original object up to my ability to draw them. So this is an image. And in fact, it's a virtual image. And what makes it a virtual image is the fact that the light rays aren't actually coming from here. They only seem to come from here. Right? So what I get is a coherent locus of coherent point where light rays appear to come from, and it's located on the far side of the mirror, which I know that there's no actual thing on the far side of the mirror, so it is a virtual image. Right? Okay, so that's a location where light rays appear to emanate from after they interact with the optical element. The optical element is just kind of stand-in for lens or mirror. In this case, we got a mirror, and a plane mirror at that. So one bit of terminology, brown chalk won't work, and one new piece of information. So we actually have this image, and we have this object, and we can start coming up with this kind of standardized terminology for how we'll talk about some of this stuff. So this, from here to here, is what we'll call DO, the object distance. From here to here, this is DI. We'll call this the image distance. And from here to here, we'll call that the object height, denoted H naught. And from here to here, we'll denote that as the image height. And honestly, it only took us 2 light rays. It turns out we have a complete analysis of plane mirrors. So in the most advanced and professional sounding optics jargon that I can muster, what I would say is that plane mirrors form virtual images that satisfy the following. And there's going to be like one quirk to this. These absolute value bars. So I'm putting absolute value bars on DI because it turns out that this is going to be on the negative side. So the positive side of the mirror is going to be in front. So if, this isn't really, this isn't a distance. What it really is a location, which means it would carry sign information. Positive if it was on the same side as D naught, and negative if it was on the opposite side. But for this, we see that D naught is DI and H naught is HI. So my picture is not really amazingly to scale, but probably shouldn't need too much help to convince yourself that this is true. So what we could do is, for instance, observe that these are opposite angles. So those angles are the same. And then if I note that this is a similar triangle, what I get is opposite interiors, and this triangle and this triangle and that triangle and that triangle are all not just similar, but they're the exact same triangle because they're similar and they share a side. So this is a purely geometric argument, but hopefully nobody's like too shocked by that. So we'll do some tricky stuff in the in our problem-solving sessions. But mostly what I want to do is run through this to introduce some of the terminology. So object distance from the object to the mirror, image distance from the mirror to the image. This could carry a sign, SIGN sign, either positive or negative, depending on whether or not it's in front of or behind the mirror. And then H naught and HI. Right? And when we get to something that's more interesting than a plane mirror, we'll introduce the idea of magnification, lateral magnification, which is the ratio of the heights. So how much the thing is stretched or squeezed. Okay. So this is a good point to check in with like real life and maybe ask, what on earth does this have to do with non-ideal things? And you might remember this. The question was, how tall does a mirror need to be for a person to see their entire height? And here's a lot of mirror, maybe more than we need. And here's a person. And they're doing physics, so they've got kind of a neutral face. So to use this object and object concept, what you have to realize is that this is not one object with like a height that's this big, and I don't draw a single arrow that describes this. Really what's going on is that light is being emitted from everywhere, all over the person, his or herself. And I can draw a light ray from here. This is one object. I can draw a light ray from here. This is another object. And to get kind of a rough answer for that, the question of how big this mirror needs to be, what we did in, what are we calling this, Zoom lecture? Was realize that, okay, I can bring a light ray in towards the mirror. It's got to come back and hit my eye. You know, pretty close to true is that we've got a light ray exactly like this, right? So it comes in pretty close to parallel and it leaves pretty close to parallel. And then I have another object that could be considered this point where light is leaving my shoe. And what I have to do to get to my eye, which is at the top of my body, is basically bisect the mirror. So halfway in between top and bottom. So I've got to bounce this off of that. Equal angle of incidence and refraction. There's theta I, there's theta R. And how much mirror did I actually need to do this? Really just half. And to prove that it's about half, I can actually use this trig, right? So because these are two similar triangles, right angles, equal angles, which means the third angles are equal, and they share a side, then they have to be exactly equal. So these two triangles are not just similar, but identical triangles. So this height has to be equal to that height. Therefore, the person has an entire height of h. That's got to be h over 2. That's got to be h over 2. And that means that's got to be h over 2. Did this depend on how far away the person was? Nope. So if I draw somebody that's much, much farther away, I would get the exact same thing. So now the light ray would come in, and what would change is this angle. So by being farther away, the angle would be shallower. And when we talk about a little bit about astronomy and magnifying glasses, these angles will basically shrink to 0, but you still have some of the same geometric results, is that this is just being cut in half again. So we'll say about half. All right. And this is the style of argument that you'll do a couple of times. Basically, all this stuff from trig that you may have forgotten about, you know, opposite interior angles and similar triangles, for instance. And we'll go through a couple of you know, more substantive problems with that. Okay. So let me just drop a couple of more definitions, and then we'll pick up with more interesting stuff, spherical lenses, in the next little mini lecture. So this is going to be true for all mirrors. Lenses have their own, and the price that you pay for having only one spherical thingy equation, one lens or mirror equation, works for both, is that the signs are different for lenses and mirrors. So something's got to give. So the sign conventions for mirrors are that there's a positive side and a negative side, and a positive direction for up-down and a negative direction for up-down. And they're completely defined by the object itself. So here's the object. If the object looks like this, then that means that this is the positive side. And anything that's upright is also positive. And so what we discovered is that when we made an image out of this, the image showed up here. So there's the image. This is the negative side. And this is positive because it's upright, so this is positive, positively oriented. So what that would mean is when I work out the actual numbers, so d naught, let's just put some numbers on this. Let's pretend that I measured it. Let's say that that's 30 centimeters. So if d naught is 30 centimeters, and that's about 5 centimeters, so h naught, the height, is 5 centimeters. Then, using our sign conventions and undoing that absolute value bar, this is on the opposite side, so this is negative, so di would be negative 30 centimeters. Plane mirrors don't magnify and they don't move, so we had these two nice similar triangles. And because this is upright, the image height would also be positive. Okay, so this is going to work for all lenses, and later when we do some spherical lenses, I'm not going to tell you what's in the mystery box, but I'll draw a mystery box. So there's a mystery mirror inside this box. I'll draw my principal axis. I'll draw an object. And I'll skip the ray diagram because we don't know how to draw those for anything that's not a plane mirror yet. And let's say that I get an image here. And it turns out it's a real image, so it's not virtual. So the light rays actually bounce off and they actually go through this. And we'll define real image when we see one properly with convex mirrors. Actually, with concave mirrors first. So here, d naught is positive. This is actually always true. In fact, d naught defines positive. H naught is positive because it's upright. But now di, because it's on the same side as this, is also positive. So same side as object. And then hi, because this is inverted, is negative. So upside down. So those are the sign conventions. And what we're going to do is we're going to derive a formula that makes these sign conventions just make the formula, kind of plug and chug, easy to use. And all you have to do is know this and know how to interpret them. So let me make one last, qualitative comment, is that we distilled everything down into these ideals of perfect objects and plane mirrors. So what's going on with an actual surface? And I'll uncartoonify stuff. I mean, this is still like a cartoon, but it's slightly less cartoony, I guess. Here's a wall, right? So there's a painted stucco wall, and here's a light bulb that's emitting light. And the light bulb, we'll just draw some rays coming off. I know that stuff is reflecting off of this, but I've never seen a reflection of a light bulb in a white painted wall, at least if it wasn't super high gloss finish or something. So what is going on? So what isn't going on is we're not breaking the law of reflection. So the law of reflection is still totally valid and totally working. What's actually going on is that if I were to zoom in way, way, way far on this, individual light rays are still bouncing off of the wall and being reflected, but light rays, because their wavelength is so teeny, 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 tiny, every single bump in the surface is like a giant mountain to them. And so light rays that would come in parallel and in a plane surface, like a polished silver mirror, would come off parallel to each other. Now what's happening is they're going to experience all sorts of wild different behavior. So I'll obey the law of reflection, which is true. This thing does obey the law of reflection, bounces off like that. This thing, so here's normal, coming off like that, bounces off like this, and then this thing hits that. Here's normal, bounces off like that. So basically it gets scattered all over. So it's not that the amount of light that hits a white wall is different than the amount that comes off of the white wall. What's actually true is that it's just not forming a coherent image because it's not flat. And not flat means not flat on the, the size of the wavelength of light itself. Okay, so the two words for this are called diffuse and specular reflection. So what this is an example of is what's called diffuse reflection. What's true is for each one of these, theta I equals theta R for sure. But what's not true is that the surface is smooth on the order of the wavelength of light. So draw this down there. And again, if you remember the introductory discussion, the wavelength of visible light is, roughly speaking, 1/10 of 1 micron. So it's teeny tiny, which is, it's almost like a miracle that polished mirrors work really well, and that's why they've got to be metals. What this is when we have, for instance, the analog of this with a flat material that's really highly polished to the point where it doesn't really have bumps on this order. So we'll just kind of copy this drawing. So if I zoom way in on this, I get what's called specular reflection, where light rays that come in parallel leave parallel. And so when your eye is sitting out there, you basically get a coherent image of the thing that was that emitted the light in the first place. So this is what's called specular reflection. And honestly, this explains why you're able to listen to radio transmissions that bounce off the atmosphere, because radio transmissions have wavelengths of light that are like 1 meter. So they can bounce off of chunky things coherently, which is kind of nice.